Good morning to everyone. I'm Dr. Sumi. The topic of my today's presentation is power dissipation in CMOS from Unit 2 Combinational Logic Circuits. On completion, the students will be able to build low power consuming ICs with reduced power dissipation in CMOS circuits and also be able to describe about dynamic power dissipation. Power dissipation in CMOS. The two components that contribute to power dissipation are given as static power dissipation and dynamic power dissipation. Static power dissipation includes the leakage current as well as the sub-threshold current, whereas dynamic power dissipation includes short circuit power dissipation, charging and discharging power dissipation. The instantaneous power consumed by a circuit element is the product of the current and voltage of the element, that is P is equal to IV, or we can write P of t is equal to I of t into V of t, and the energy consumed over a time interval capital T is the integral of this instantaneous power, and we can write E as an integral of P of t dt ranging from 0 to time t, and the average power can be obtained from this energy consumed divided by the time interval t. P average is equal to E by T, which is equal to 1 by T integral P of T dt. Here the power is expressed in units of watts, whereas energy is usually expressed in units of joules. By Ohm's law, we know voltage is equal to the product of current into resistance. V is equal to IR. So the instantaneous power dissipated in the resistor can be given as PR of T is equal to V square R of T by R, which can also be written as I square R of T times R. This power is converted from electricity to heat. The supply voltage VDD supplies power proportional to the current, and the power with respect to the supply voltage P VDD of T is given as I dd of T into VDD. When this capacitor is charged from 0 to a voltage capacitor voltage Vc, it stores an energy EC. EC is given as integral I of t V of t dt, and substituting the values we are getting the energy stored as half C Vc square. The following diagram represents a CMOS inverter driving a load capacitance. Here VDD is the supply voltage and the load capacitance CL connected across the output side, and we are giving an input Vin to both the PMOS and NMOS and getting an output Vout. When the input switches from 1 to 0, the PMOS transistor turns on and charges the load towards the supply VDD. According to the energy equation, the energy stored in the capacitance EC is given as half CL Vd square. The energy delivered from the power supply is given as EC is equal to integral of I of t Vd t dt, which is given as C Vd d square. Gate switches at some average frequency f of SW over some time interval t, the load will be charged and discharged t times this average frequency, that is t into f of f suffix sv times. Then the average power dissipation is given as the switching power, which is equal to E by T, that is substituting the values we get C into Vd d square f of sw. This is called the dynamic power because it arises from the switching of the load. Because most gates do not switch for every clock cycle, it is often more convenient to express the switching frequency f of SW as an activity factor alpha times the clock frequency f. So we can rewrite the above expression as power of switching power as alpha C Vd d square f. The activity factor is the probability that the circuit node transitions from 0 to 1, because that is the only time the circuit is consuming power. A clock has an activity factor of alpha equal to 1 because it rises and falls every clock cycle, and hence the total power of the circuit can be calculated as total power is power dynamic is equal to power switching plus short circuit power, and power static is a combination of subthreshold current plus gate current plus junction current plus contention current multiplied with the supply voltage VDD, and as a whole we can write the total power as power dynamic plus power static. This dynamic power can be written as switching power, which is equal to alpha C VD square F. The supply voltage VDD and the frequency F are known by the designer, and to estimate the dynamic power one can consider each node of the circuit. The capacitance of the node is the sum of the gate, diffusion as well as wire capacitances on the respective node, and the activity factor can be estimated using switching probability, or it can be measured from logic simulations. The effective capacitance of the node is its true capacitance multiplied by the activity factor, and the switching power depends on the sum of all the effective capacitance of all the nodes present. Quiz questions on power dissipation in CMOS. Power dissipation is directly proportional to the supply voltage, square of supply voltage, square of capacitance, square of input signal. The answer is square of supply voltage. How do you calculate the total power of a circuit? Thank you.